So our next speaker is Bertram Bitsch, who will introduce the ChemComp code. Go ahead, Bert.
Yes, thank you very much. So I want to introduce the ChemComp code for calculating disk and planetary compositions. So the motivation essentially was driven by the observations of exoplanets. Of course, you all know this kind of plot, so planetary mass against orbital distance. In color, the guys from the exoplanet observations. In black, our friends from the solar system. Of course, we can we're focusing mostly in this code actually on Jupiter mass planets. So we have the two groups, the cold Jupiters and the hot Jupiters. And there's, of course, this underlying question related to the hot Jupiters. Where do these planets actually form? Because in the inner regions of the disk, it might be way too hot, like above 1,000 Kelvin or even hotter, where the small dust grains actually start to evaporate. And it might be very, very difficult to make the first building blocks, pebbles, and planetesimals in this region. So the question is really, where do the giant planets form in these scenarios? And we can relate this to two main scenarios where the idea is you have maybe some cold Jupiters that you form in the outer regions of the disk, and then you scatter them inwards, where they become hot Jupiters by tidal separarization. Or you have maybe some planets where you form the planetary core in the outer regions of the disk, and these planets smoothly migrate inwards and accrete gas on the way to become the hot Jupiters. And then, of course, there's the underlying idea that maybe we can actually relate it to the chemical composition of these planets, because in this paper from Oeberg 2011, the idea was that maybe different regions in the disk related to different evaporation fronts will exhibit different compositions, and the planets forming in these regions will then inherit these compositions. You see here in this plot two lines. So the black line corresponds to the solid composition, and the dashed line corresponds to the gaseous composition, right? So in the outer regions of the disk, it's very, very cold, so everything is frozen out. So in this case, we would have a solar-like composition for our ices. But the moment we go in towards the inner regions, where it becomes hotter, the ices will evaporate and release their volatile into the gas phase. So for example, at the CO evaporation front, we release CO ice into a vapor. So we have CO vapor, and then this means for the gas, in this case, we have, of course, a C/O ratio equal to 1. And then as we go inwards, other species like CO2 or water can evaporate, and the CO/O ratio will change on the way. And the idea, the classic idea is, of course, can we map the exoplanet composition to the location in the disk? And the question is, of course, is it really that simple that we can use that picture? The answer, of course, to that is no, because I have a few slides left, and we're building this code. So the idea here is we have a full planet formation model. So this is the flow diagram, essentially, of our ChemComp code. So we have a 1D viscous disk evolution model. So it's a radial grid. Inside of this grid, we have a pebble growth and drift model that is based on the Birnstiel 2012 work. The idea here is that we have small micrometer-sized dust grains. They can then grow by coagulation and drift. And additionally, what we built into the code is a pebble evaporation and also recondensation at Iceland. So when the pebbles cross evaporation fronts, they will evaporate and release their volatiles into the gas phase. At the same time, the vapor can diffuse outwards and recondense and make new pebbles at these evaporation. We have a very simplistic chemical partitioning model. So we take the initial composition that we assume regarding the different atoms like carbon and oxygen, and then we partition this into our molecules, like how much water do we have, how much CO, CO2, and so on. And this is something you can actually change very, very simple in the input file of the code. We have no chemical reactions within the code. Additionally, from a planetary side, our planets can grow by the accretion of pebbles. We can accrete by gas, where we are limited by what the gas disk can provide. And the planets migrate through the disk in type 1 or type 2 migration, depending on their mass. The code in itself is fully written in Python. So if you're a Python lover, you will have it easy to understand the code. The code is actually relatively fast because it's a 1D evolution model. So we have a typical runtime of around 30 minutes for 1 megayear of evolution on a single CPU. And this code, we can use this to calculate two main parts, the disk and the disk structure and composition, and also the planetary composition. I will show some examples how we can do this. But before going to, I would like to give you the essence of the principle that goes within this code. And the essence is related to the fact that there's a velocity difference between the pebbles and the gas. You see here in this plot the total radial gas dust velocity is a function of the Stokes number. So the Stokes number essentially is just a measurement of the size of the particle. So this is goes back to the Brouwer 2008 paper. So the dashed line corresponds to the gas velocity, and the black line corresponds to the dust velocity. So if you translate the Stokes number into sizes, so the small micrometerish dust grains, they are perfectly coupled to the gas. They will follow the motion of the gas. While the larger pebbles, they will actually decouple from the gas and drift inward very fast. And the reason for that is because these pebbles feel a headwind from the gas that robs them of angular momentum, and they can shoot into the inner regions of the disk. And you see here, and for this example, if you look at the pebbles of typical orders in protoplanetary disk with Stokes number of around 0.1 up to 1-ish, you see that there's a few orders of magnitude difference in the velocity between the gas and the dust. And this has consequences for the composition of the disk. So first, a little bit of motivation why we do not include the change of the chemical composition during the pebble drift. This is related to this work from Eistrup and Henning, where they start with small pebbles in the protoplanetary disk that drift inwards. So they drift here towards the left to smaller distances. And the different colors correspond to different molecules that are basically attached to these pebbles. And if you follow the small dashed line, which is the most realistic pebble speed, you see that these lines, they are basically constant up until a certain point where they have a rapid drop. And this rapid drop is related to the position of these evaporation fronts. For example, you see a drop in the CO2 composition of the pebble at the CO2 evaporation front. So the CO2 ice evaporates, and then of course we have no CO2 left on the pebble. This happens basically for all the species, but you see that there's essentially no change in the composition of the pebbles during the drift stage. Now, the consequence of this is that we can see a pileup of vapor interior to evaporation fronts. You see here in this plot the time evolution as a function of orbital distance for the water content within a protoplanetary disk. So in the outer regions of the disk, it is cold enough that water is frozen out, so we have water ice, so we have no water vapor. And in the inner disk, the water ice can evaporate, and we'll have water vapor. So what happens is, in the very early stages, your pebbles, they start growing, and then they start to drift inwards, and then they will evaporate close when they cross the water evaporation front, and they will release their volatiles into the disk. Now, this will cause an enhancement in the water vapor compared to the initial amount of water vapor because of the velocity difference between the gas and the dust. So the pebbles go in very fast, they evaporate, they become gas, and suddenly they're moving much, much slower. So we can actually get a pileup of this vapor close to the inner regions of the protoplanetary disk. In time, this water vapor will then slowly diffuse inwards, and we can get an enrichment of the inner disk with water vapors up to maybe like an order of magnitude more compared to the initial value. So we can have a pileup of water vapor in the protoplanetary disk. Consequently, this directly means that the disk composition will evolve in time, and this is very different compared to the original picture from ÖVAC 2011 that I was showing you before, where this is a static picture. So we have a time evolution of the compositions of the protoplanetary disk. To illustrate this a little bit more, so this plot shows you the C/O ratio in the protoplanetary disk as a function of time. So the vertical axis again corresponds to the time evolution, and the x-axis is the radial distance. So essentially, if you want, you would take a cut through the disk at t=0. This would correspond to the ÖVAC picture that I showed you before. So the exact step functions at these evaporation points. But in time, we see a clear evolution of the C/O ratio due to the inward drift and evaporation of pebbles. So for example, we see here that this becomes very, very bluish, which means we have a very low C/O ratio interior to the water evaporation front, because the water ice-rich pebbles, they drift inwards, evaporate, release their water, and therefore the C/O ratio drops. In the outer regions of the disk, we have an increase of the C/O ratio because of the methane ice, and that of course has no oxygen, so the methane ice goes in, it evaporates, releases the carbon, we get a very large C/O ratio. Now we can use this to also for different stars in order to understand the difference in the inner disk chemical composition. So there's from observations, we know that the C/O ratio in the inner regions of around M dwarfs should be more carbon rich compared to solar type stars. And this is exactly what our model shows. So you see here 5 panels corresponding to the 5 different stellar masses. So we go from 1 solar mass all the way down to 0.1 solar masses. And what you see is a difference in the inner disk chemical composition, especially for these very small stars. We see that we can actually reach the reddish kind of curve, so like a supersolar C/O ratios after like 3 million years. And the reason for that is that these disks are colder, because the star is smaller, we have a less luminous star, so the ice are actually closer to each other. So we actually accelerate the effect of the pebble drift and the vapor transport around these disks. In particular, the carbon-rich material can make it to the inner disk on much shorter times compared to the solar types disk where the vapor has to be transported over a much longer distance. Of course, this whole thing is a function of the disk's viscosity, because the viscosity sets the velocity of the gas. So in the bottom panel, we have now an alpha viscosity of 10 to the minus 3 compared to 10 to the minus 4, what we have on the top panel. And you see that also for the solar type stars, we could get a carbon enriched disk. So it depends clearly on the viscosity in the disk that transports the vapor. But this is, of course, a parameter we can change in these simulations. But in order to be consistent with observations in a low viscosity picture, we can actually explain the observation of these carbon-rich inner regions of protoplanetary. Now, moving towards planets, the idea here is that we want to compare the composition of the planetary atmosphere that is measured with our simulation. So you see here an example for two planets that have been observed, Tau Bertram B and WASP 77AB, in respect to their carbon and oxygen composition. So this is normalized to the stellar composition, and we have the C/O ratio on the right. And the question is, of course, when do these planets form? So we have one guy supersolar and one guy subsolar in composition. So what we then do, we can run our simulation, a lot of these different simulations, where we have to cross off the planet. So you see these so-called cross tracks. So this is the evolution of the planet in the semi-major axis mass plane. The solid line corresponds to the solid accretion, so pebble accretion, and the dotted line corresponds to gas accretion. So as the planets grow, they migrate and they can cross different evaporation fronts, and this will allow them to accrete different materials. So for example, the planets that will grow migrate into the inner regions of the disk, and they cross the water ice and will accrete a large fractions of oxygen from the water vapor. So these planets will be very oxygen rich. So in order to understand where the planets can form, we can test many different parameters, so like the different positions in the disk, also different viscosities. And then in the end, we can match this to the observations. So the dots here correspond now to the best fit of our simulations. So this scenario, this pebble drift and the evaporation model allows this super and subsolar carbon and oxygen abundance. And this depends on the formation position of the planet. So in the inner regions of the disk, as you have seen in the example for water, we can reach supersolar compositions, not only for oxygen, but also carbon. In the outer regions of the disk, we will remain subsolar in composition because the pebbles, they stay frozen out, so the volatiles are still frozen, and then they will accumulate exterior to the planet, because the planet exerts a pressure bump as it grows, and these pebbles can then not be accreted onto the planet, and the gas remains subsolar, and thus the planetary composition remains subsolar. In this case, we could deduce the formation or location of these two planets from beyond the water and from beyond the CO2 evaporation from. This is very interesting. I think also considering that the measured C/O ratio for both of these planets is actually the same. So the point here is also that the C/O ratio alone might not necessarily tell you the formation location of the planet. So you have to go into more detail. To summarize, from a physical point of view, so the inward drifting pebbles will evaporate and enrich the inner regions of the disk. We are not the only people that claim this. So there's also older papers from Richard Booth that studied this. The other important point is that the disk C/O ratio changes in time, so it's not static, and also that the C/O ratio alone is not a tracer of the planet formation location. From a computational side, so ChemComp can calculate the pebble drift and evaporation to determine the disk composition. But you can also use it to calculate the planetary growth and also the composition of the planet. The code is publicly available on GitHub. We also have a wiki that can guide you through the different options of the code. The code is written also very modular, so there's different add-ons that I also didn't talk on, and they are not publicly available. So, for example, we have a student, Julia Lina, that works on photo evaporation within this code. If you're interested in this, we can of course talk about it and also release it to you. Or of course, you can adapt the code by yourself. Thank you, and I'm happy for any questions.
Thank you very much, Bert, for a super nice talk. And indeed, it's time for questions. Yes, Peter?
Yeah, thank you. You explained how you get an oxygen enrichment first, but then as you explained, I think if I understand correctly, the tendency to produce in the finally a carbon-rich inner disk is always there. It just takes too long for normal Tauri stars, right?
Yes, it depends on the viscosity, right? So you see here on the right, so on top you have the alpha 10 to the -4, on the bottom you have the alpha 10 to the -3, and there we could also get a carbon-rich inner disk. The viscosity here has two effects. So the first is it transports the vapor more efficiently if you have a higher viscosity, so you get rid of the water vapor earlier on, and the carbon-rich material from the outer region can make it carbon-rich vapor can make it into the inner disk faster. So there's the two effects that into a plate. In order to get the largest C/O ratio, you can basically remove the oxygen and then it will go up, or you can add carbon on it, right? So there's the two ways that basically that are accelerated by the viscosity.
Yeah, this I didn't quite understand. I mean, you explained how you get the water enrichment, but how do you then turn it around and finally get a carbon enrichment? Can you explain that once more?
Yeah. Yes. So the water vapor that we generate in the disk is transported away by the gas. So and this means we will reduce the oxygen abundance in the disk. But at the same time, we still have like some carbon abundance in the inner regions of the disk, of course. And we have for example, the CO or methane from the outer regions of the disk that will slowly make it towards the inner regions of the disk. So we take oxygen away and replenish it with carbon that comes from the outer regions of the disk. This is, of course, depends on the viscosity. So higher viscosity will accelerate that process. In addition, the growth of our pebbles is limited by fragmentation, which is also a function of viscosity. So at low alpha, we have larger particles. So we will basically grow the particles to larger sizes, and they will drift inwards faster, which will result in a larger enrichment of oxygen in the inner regions of the disk. So you can see this maybe a little bit in the bluish color. But at this, and if you have the higher viscosity, we'll have smaller particles, so the enrichment in itself will actually be lower. So we have to basically erode a smaller mountain of oxygen, so to say, if you have the higher viscosity, and that basically adds up to this effect.
Yeah, thank you.
Another question from Richard. Richard, go ahead.
Hi, Bert. Thanks for a really nice talk. Have to say I agree with most of what you said here. One thing that I do think actually is important is potentially the impact of chemistry on the gas phase abundances on these long timescales, right? So I completely agree with you that these drifting pebbles mean that the pebble composition doesn't change very much in the time they go from, say, 20 AU to 1 AU or something like that. But over the 3 to 5 million years that your gas is drifting in, actually the chemistry can do quite a lot.
Yes, we do not include the gas chemistry. Of course, there's another caveat in this, also related to the pebble chemistry, because the moment you have a planet and will open a pressure bump and you accumulate your particles in the pressure bump, and they will happily sit there for like a few million years, then of course also chemical reactions will become important. This is something that is not included in the code at this stage, of course, but it's something that we should work on, absolutely.
Thanks, Bert.
Thank you.
Okay, are there any more questions? Doesn't seem to be the case. Well, then, Bert, thank you very much.
Thank you.